Okay. All right. I think we can get started. So this is our last workshop. You want more? No. Okay. Wow. Okay. So this one is just about the business applications of derivatives. So from the previous 2 lectures, that material we'll be talking about. If we have time, then there are more derivative rules. There are always more rules. We have not talked about these ones in class. So they're kind of the next things you would learn when learning about calculus. So if we have time, we'll talk about that stuff. If we don't have time, then we'll just focus on the business application stuff. That's the more important thing to practice. So we'll see how things go, how much time it takes, and what questions you guys have. Okay. I don't have any review slides here, but we remember our process and which derivatives give us which information, and then substitute those values into what, all that. Okay, maybe. We'll see. All right, here's the first one. So it's a word problem. Take a bit of time, read it, see if it makes sense to you. Before you start doing any math, though, we'll talk about it because it's a little different from the ones we've done. But just read, see if you can understand. All right, so let's talk about this. So company is making something. These things, a garden conservatory, it's like a kind of a greenhouse or something people would build in their backyard. It's like rich European like houses or whatever, not a common thing. Anyways, we have this equation, and what does it represent this year? Costs, okay. So they've given us a definition here. So X is the monthly output. What letter, what variable did we usually use for that in class? Q. So just your production quantity. Okay, so this is from a different textbook, so their style of presenting this is a little different. So that X here is Q, and here, where the Y is the cost per conservatory in pounds. So the cost, the currency there. So what does y represent? Which kind of cost? Sorry, louder? You changed your answer? Which one? Is this total cost or is this marginal cost? So this is the part, the cost per unit, cost per conservatory. Okay, this is the marginal cost here. So they have not given us a total cost equation. This is the per unit cost. So remember, for these total cost curves, it's not just linear, it's curved like this, because our production gets more efficient. When we make, the first one, our per unit cost is this, but when we make number like 500, we're a lot more efficient, and then the cost to make number 501 is less than the cost of making the first one. So we're getting more efficient as we go, and this is representing our per unit cost here, so marginal cost. We can see this is a positive quadratic, so it would look like this. This is the basic shape. So we have this kind of low point here, and then it starts getting inefficient and it starts going up. So we would normally look at these total cost curves or we would normally look at it as total cost, but the derivative of total cost would look like this. It's a quadratic like this. Okay, so it's the same style as the problems we've had, just we're starting at a different point here. So question A, find the least cost level of output. So the lowest per unit cost. How would we find that? Okay, so derivative. So if this is marginal cost, we want lowest point, then we just, we have our process for finding turning points and checking if they're minimums or maximums. So we find our derivative of the marginal cost. But derivative of marginal cost is second derivative of total cost. Those second derivatives are inflection points. So it's really the exact same thing we did in class. Find the inflection point. It's just stated a different way. Okay, so that's what A is. And B is, we'll come back to that a bit later. And then, so A and C. So find the minimum, the location of the minimum marginal cost, and then the actual minimum marginal cost. Okay, so those two things, please try to do now, and we'll talk about them when you're done. This thing is already derivative and solve. All right, we got lots of people finished. Similar answers, at least for the first part. For part C, I saw some different answers. Okay, same information, I just condensed it a little bit so I would have room to write here on my slide, but same thing. So I'll rewrite the information they gave us, marginal cost in like the way that we usually write it. So marginal cost is equal to 2q squared minus 280q plus 16,000. Okay, so just kind of adapting it to what we are more familiar with. And we want to minimize this, so we find our derivative, marginal cost prime, for q minus 280. And if we set this equal to 0, then 0 is equal to 4q minus 2, 80, and q equals 70. So I saw the same number from everyone. We got the same number here in the chats. Part C was a little different though. So let's see. Part C, I didn't label this A. Part C. We're trying to find the actual minimum cost per unit. So we have this location here, 70. Which equation should we use to try to find the actual minimum cost per unit? Okay, so this original marginal cost equation here. So if we substitute into here, when Q equals 70, marginal cost is 2 times 70 squared minus 280 times 70 plus 16,000. So this is where I saw people having lots and lots of different answers. I saw 62,000. I saw lots of you had, was it 7,400? 7,900? 7,400? Okay. Chat, we had 25,800. Okay, so we're all getting very different numbers here. Okay. So 2 times 70 squared. Okay, 4,900. Here, I don't want to have to do this directly. Can you see a shortcut I could do? What? Okay, okay, there are lots of shortcuts we could use. I was thinking similar to this one. What do you see? Okay, so this is, 4 times 70 squared, and we already figured out what that is. So really, we just have negative 2 times 70 squared, 4,900, plus 16,000. Okay, so negative 9,800 plus 16,000. 7,200. Sorry, 6,200. Sorry. I was looking at the wrong thing. 6,200. Okay. Okay, does this seem correct to everyone? We did get lots of different answers for C. This seems okay? All right. So part B here was asking us to just verify that this is actually a minimum and not perhaps a maximum. How would we do that? Okay, second derivative. So this is a thing we didn't do in class. It's like marginal cost double prime, sort of a third derivative of the original cost function. But if we did that here, we would just get, well, 4. 4 is greater than 0. If it's greater than 0, we are dealing with a minimum. So yes, it's actually a minimum. Just to give you a sense of what these graphs look like, let's do pink. So the total cost function, there is actually a way to figure it out from this. You could just do like the derivative rule, but in reverse, which we haven't done, but that's another big area of calculus. So if this was the original function, sorry, total cost, then the marginal cost function would look something like this. Okay, so it's a quadratic, and then the marginal cost prime, which we did in green, would be a linear equation like this, and then this last one here, this third derivative, would be just a flat line at 4. So from a cubic to quadratic to linear to just flat. Our exponent keeps reducing by 1. These I didn't make the actual proper graph for this because when we have 4 different layers, it gets really confusing. If that's hard to understand, don't worry about it, but just trying to give you some sense of what's happening here. Okay, question? I have not asked, like, from this, for example, any of it? I have not asked you to, or like in class, we haven't talked about like, you know, here's an equation of a cubic and then make a graph of it for me. We haven't done that. But we have talked a lot about comparing an original function and its derivative. So I could say, here's an equation, and here's the graph of the original function. Sketch just a basic view of what the derivative would look like. Here the slopes are positive, so the first derivative must look like this. Here the slopes are negative, first derivative must be, you know, like positive or negative. It's kind of a basic sketch like this that we should be able to do that. Okay, any other questions? We did B here. Because we found the turning points, we found the minimum, and then we use this second derivative of marginal cost, like third derivative of total cost, to verify that it was a minimum. Any other questions? Okay, next one is here. So again, take a moment to read it. It's a little different from what we've had. Then we'll just make sure we understand the word problem, and I'll give you time to work on it. All right, so this equation here, what does it represent? Okay, so yes, this is our revenue equation. So if we were to rewrite it in the way we are familiar with, TR equals -4 P. This one says X is the selling price. So P squared plus 960 P. Okay. So in this case, usually we were looking at these in terms of Q. Here we don't have a cost equation we're trying to combine it with, so it doesn't really matter. We could work backward and change this to be in terms of Q, but the question gave it to us in terms of P, so we'll just work with it that way. So we want what price will maximize revenue? We're going to give everyone time to work, okay? So what price would maximize revenue? Confirm that it is actually a maximum with your second derivative, and then find the actual maximum revenue. All right, so again, same question. I've just shrunk down the information a bit so I have space to write. So we have our total revenue is equal to -4, sorry, not Q, P squared plus 960 P. What was the first part A here? What price will maximize revenue? What did you find? 120, okay. And what was the actual maximum price? 57,600, okay. All right, so marginal revenue here would be -8P plus 960. And we set this equal to 0, so 0 is equal to -8P plus 960. So P is equal to 120. 8 times 12 gives us 96. All right, and we want to confirm. So we find our second derivative here. So our derivative of marginal revenue. And if our marginal revenue is this, then our second derivative is just -8. And if it's -8, that is less than 0. So we are sort of curving down, concave down at that point, which means that yes, this must be a maximum point. Okay, so that was A, to find this point here, and part B was to confirm that it is a maximum. And then to do part C, we are going to take this value here and just put it into our total revenue equation. They're asking for total revenue. We have an equation for it, so we just use that. So total revenue at this point, 120, is -4 times 120 squared plus 960 times 120, and we just work out what this is. My way of doing this again, it's a quadratic equation, so there's always kind of a symmetry with it. So this is -4 times 120 squared. And this 960 would be what times 120? 8. So 8 times 120 squared. Again, with this symmetry, often one of the numbers will be half of what the other number is. That will happen a lot. Okay, so we have 4 times 120 squared, 12 squared is 144. So 4 times 14,400. And yes, 57,600. And that was part C. Questions? Good. All right. All right, last one of this set here. So a bit longer. This is a little more similar to the ones that we've been doing in class. There are a bunch of parts here. So profit equation here. It's asking us to find a profit equation and then find the, we want the Q value and also the price that will give us the maximum profit, but then also the actual maximum profit. And then part C is just confirming that it's a maximum point. So how do we get the maximum profit and what is the maximum profit given these two things? All right, go ahead. I'll let you try to solve the whole thing. Okay, so first, we need a total revenue equation. What is our total revenue equation? In this case. Okay, so 500 Q, and again, Q here they've called X. So 500 Q minus 3Q squared. We have our demand equation. So if like price is equal to this, so again, total revenue is P times Q, and this is P. Just substitute that in, multiply by our Q, or again, they've called X here, we get total revenue. Second step, costs they've given us, I'll just rewrite in our style just for familiarity. We have Q squared and just change the order to match the exponents. Q squared plus 20 Q plus 150. All right, then we can make a profit equation. Profit is our revenue minus our cost. So if we put those together, what is our profit equation? Okay, so I'll call it Q here, just to match the labels here. Okay, 4Q squared. Okay, so plus 480Q minus 150. There is our profit equation. And we now want to find our maximum profit. So we find our first derivative. We want to find our turning point, so zeros of our first derivative. So we find our first derivative first. And what is that? Negative 8Q. Okay, plus 480 here, and we will just set all this equal to 0. I'm going to be a little lazy here and just write it like this. So 8Q plus 480. And based on that, Q is equal to what? 60. Okay, so there's the Q value. There's the output that will produce maximum profit. They have also asked us, actually, I guess it's a little, to me, it's a little weird, like verify that it's a maximum at the end here. Probably makes a bit more sense to do that first. So actually, let's just do that. Let's make sure we are dealing with a maximum. So our profit double prime, second derivative here is just negative 8. Derivative of this thing. That's less than 0. So yes, this function here, the whole time it is curving down. It is concave down. So any turning point there must be a maximum. Okay, so there's the output that maximizes profits. We can find the price that maximizes profits with our demand equation here. So we were told P equals 500 minus 3Q. And we have Q, so 500, or right, so when Q equals 60, P equals 500 minus 3 times 60, which is? Okay, so 320. There's the price that will maximize our profits. And it would be nice to know the actual maximum profit, which we had, I need a new color, light green. Yeah, we can see that. All right, our actual max profits will happen when Q is equal to 60. So that would be negative 4Q, sorry, not Q, 60 here. 60 squared plus 480 times 60 minus 150. Okay, so this is quite similar to the last one. We can notice this here. For 480, can we make that into something times 60? 8. Yeah, so this is 8 times 60, and we have negative 4 here. So this whole thing simplifies into just 4 times 60 squared minus 150. And what is our final number here? 14,250. That is our maximum profit. Sorry, a little bit louder, please. Yep. Total revenue here. Why is it not, sorry, 480? This is the demand function. So this, what we were given here, that's this. This is the relationship between demand and price. If price goes down, we sell more things. If price goes up, we sell fewer things. So this is a demand function, and it's like a linear relationship, like this. If one goes up, the other goes down. And then we know total revenue is P times Q, and we have P. P is equal to that. So we are just substituting this into this P value here. So we're just multiplying everything by Q, and that gives us total revenue. So this is the same process that we did in class. The examples from the video lecture, the recorded lecture, there were a bunch of examples where we did this, and I explained in a bit more detail. Any other questions on these? Okay, so lots of things to do here, lots of different equations to make, lots of derivatives to find, and then substitute back into different parts and get different information. So it's easy to get confused about what things we want and how to interpret those results. So just doing some practice and doing a bunch of these is definitely helpful. The questions here that we just finished. It's a little hard to see, it's down here. The linear programming practice questions that I gave you. So that same textbook, and I put like just a PDF of that chapter on our classroom page. That's the same place where these ones are from. Linear programming was chapter 2 in that textbook. These ones are chapter 3 in that textbook. So there are more of these kinds of practice questions there if you want to find them. Okay, since we have a bit of time, we get to play around with some more calculus rules here for fun. They're not too bad. I just have kind of one example we'll work through together, and then one you can try on your own for each of them. We're not going to go like super deep into them, but it's good to just have an introduction. Okay, so these are what the rules are. They look complicated now, but we'll just kind of do them one at a time, but this is the summary. So we have a thing called product rule. So remember, product is if you have two numbers together, multiplied together, the result is called a product. Quotient, if you have two things divided, then the result of dividing is called a quotient. And then chain rule is if we have nested. We have like one function inside another function. I'll explain that when we get to that one. Okay, so product rule first. Need to move this stuff over. All right, this is product rule. So let's say we have something like this. From our derivative tools we know so far, we can't directly find the derivative of this. So one of the ways we could do this is we could just expand the brackets. If we expand these brackets, we have x squared, 3x squared, so 3x to the exponent 4. And then 2 times 3x squared, x squared times 5 here. So that would give us 11x squared, and 5 and 10 plus 10. Then with here, we can do power rule directly. So our derivative, j prime of x, would be 12x cubed plus 22x, and then that's it. Okay, so this is one way of solving this, but there's another way using this product rule. So I'll show you that. So instead of expanding it, we can solve these directly. Here. So product rule says if we have two things multiplied together, then the derivative would be the derivative of the first part times just the original second part, and then the original first part times the derivative of the second part. And then you add them together, and that will be the derivative. So we'll just do this one together here. So using product rule, j prime of x, that's before we get to that. In this example, if we're doing it this way, what would our f of x be? Okay, x squared plus 2. It's the first of the two things multiplied together. And our g of x would be? Okay, it's the other of the two things being multiplied together. All right, and then our derivatives, we'll need those as well. So our derivative of f here is 2x. Okay, and our derivative of g would be 6x. So those are the 4 different parts we're going to need to put into our product rule here. So j prime of x would be, we just follow our order here. So first derivative of, or derivative of the first thing, so 2x times the original of the second part, so 3x squared plus 5, plus the original of the first part, x squared plus 2, and the derivative of the second part, which is 6x. Then we just expand and add, and we'll get our result. So if we expand the left part here, we would have 6x cubed plus 10x. Expand the right part, we would have 6x cubed again, plus 12x. And we can see if we just combine our terms here, we get 12x cubed plus 22x. And that's the exact same thing we had over here on the left side. So it's another way of doing it. In this particular example, you're right, we don't need product rule. It's faster to just expand and then use our regular power rule here. But there are lots of situations where we can't do that and where we need product rule. So I chose this example here because it's easy to see the connection, but there are lots of cases where that doesn't happen. Question? Yes. Quotient rule is the other one, and there we subtract. But this one we're always adding. These will not be on the exam. Oh. Was that not clear? We haven't talked about these in class. And I said, for fun.
You didn't go over this in class.
Exactly. That's why it's not part of the exam.
That's what I thought.
Yeah, okay. Okay, just, yeah, okay, good to be clear on that. Good to be clear on that. Okay, so if we have that, then let's try that here. You can do this one. Try to use product rule specifically to try to find our derivative. Finished? Question? Finished? Finished? Okay. Other people finished? How many? Lots? Yeah. All right, let's try. So first we'll just make sure we're separating this correctly. What would our f of x be? Okay, 2x to the exponent 5, and our g of x, okay, 4x squared plus x. So our derivative then would be our derivative of the first part. What is that? Okay, 10x to the exponent 4 times our original of the second part, so 4x squared plus x, plus our original of the first part, 2x to the exponent 5, times derivative here. Okay, 8x, right? Plus 1, okay, good. So little exponent 1 here turns into this coefficient. All right, and then we just expand, so 40x to the exponent 6 plus 10x to the exponent 5 plus 16x to the exponent 6 plus 2x to the exponent 5, and that gives us 56x to the exponent 6 plus 12x to the exponent 5. Okay, if we were to just expand this directly and use our power rule on this, we would see that we get the exact same result here. Okay, so this one, product rule, not too bad, not too confusing. For sake of time, I'm gonna kind of skip over quotient rule. So I'll just very briefly show. Quotient rule is very similar, but on the top we subtract instead of adding, and then we have to divide the whole thing by the bottom part squared. So this is kind of part 1, this is part 2, then we divide by the bottom part squared. So it gets a little more complicated. I'm gonna skip over these though. You can write down the rule if you want. Chain rule is more complicated. That's the one where we maybe need to talk about it a bit. So I'm gonna go to chain rule instead. So quotient rule, very similar to what we just did, but there's a subtraction and you have to divide by the bottom one squared. Okay, all right. So chain rule. This one is more complicated because we have nested functions. We have something inside another one. So if we look at this thing, like how would we do a derivative of this? It's kind of confusing. But we can use chain rule to kind of just logically split it into two different parts that we can handle more easily with power rule. And then we can use our derivative tools for that. So the thing we have to do with chain rule is we do the derivative of the outside part with just the inside part not changed. And then we multiply that by the derivative of the inside part. So this nested function, this can get a little confusing. So let's figure this out. What would the, I need to move this down a bit. What would the outside part be here? Not just 1. Have to be a little more than that. Not the whole thing. We have to split this up into, so Almost 1 over something. So often what's easiest is kind of look at these brackets here.
1 over x squared.
Yeah, let's use that. So 1 over x squared. We can do derivatives of this. Okay, we have our power rule. We convert it to a negative exponent. We can do derivatives of that. And then the inside part would be 3x squared plus 1. Okay, so f of x, f of g of x would be f of 3x squared plus 1. And then f of x says the inside part gets squared, so that's the 1 over 3x squared plus 1 squared. So this is before we've done any derivatives. This is just understanding function notation and sort of nested functions inside each other. Okay, look at that closely. Spend a bit of time just looking at that and see if you can see how that's working. This is the outside function. This is the inside function. We kind of understanding it a bit? Okay, so this function notation, f of x, doesn't mean it must be just x. We can put anything, f of 25, f of z. It doesn't matter. We can put anything we want inside the function. It just means whatever is inside these brackets, we replace, if it's x, then we just replace the x with what's inside the brackets. So this is inside the brackets here, and we are replacing that. So 1 over x squared, but instead of x, we get rid of that and we put this in there. It's a little confusing because we're using x in each place. And the different x's kind of have different meanings depending on what the functions are. So that's the more confusing part. But we're just kind of taking one thing, putting it inside the other one. So this is just how function notation works. Okay, so if we have that, these derivatives are not too hard. So if we use this function notation, we can apply that to our chain rule here. So our h prime of x here would be, we have our two parts. Okay, so let's add one little bit here. Move all this down. What is our derivative of f of x? -2 over Okay, so let's just make sure we're understanding this. So this is x to the exponent -2, right? So this is -2, and x, I'll write it this way, -3. And then we can change it into a fraction afterward. And our derivative of g of x, this one's easy. It's just 6x. Okay, so our chain rule thing here, we would have -2, but x we have to replace with the inside function. So -2 times the inside function, 3x squared plus 1 exponent -3. So that's the f prime of g of x. That's the left part. And the right part is g prime of x, which is the 6x. Okay, so it looks terrible. Like we'd have to, do some work to simplify it and expand or whatever. But that's the basic, that's kind of rewriting this using our chain rule. After this, we just simplify it and make it look nicer. Do we kind of see where this is coming from? How many people think it makes sense? A few more, yeah, okay. So then the rest of this, we're just simplifying. So this is -2 over 3x squared plus 1 cubed times 6x. Okay, so -12x on the top. And on the bottom, we have a 3x cubed plus 3x squared plus 1 cubed, and just expand that whole thing. Okay, for sake of time, I'm not going to write out all of that. But this here, we talked about binomial expansion. Like this has nothing to do with derivatives. It's just, multiply this by that, just regular expansion here. Okay, so it's just simplifying from this point, but this step here, so understanding function notation and then how we use that with our derivative. These are the two kind of key steps to understand here. What would this be? We have coefficients 1, 3, 3, 1. So times 3 times 6, 27. 81x to the exponent 6 plus it's a little hard to do this all in your head without writing anything down. We'd have squared. Sorry. Is this one right? Is this one right? I feel like this would be 27, right? Okay. 27. Then we would have 9x to the exponent 4. Okay, and then times that's just 1. Okay, and then we would have 3x it's 3x squared and then 3x squared and then times 1 to the exponent 1. So that's 9x to the exponent 4. They have to keep reducing though. So it's 3 cubed, 3 squared, 3 to the exponent 1, 3 to the exponent 0. This one is 9. But our third term would be 3x squared to the exponent 1 times 1 squared. Yeah, I remember it too. Sorry. Coefficients here. Yes, you're right. There we go. I was forgetting about the coefficients. Okay, thank you. Okay, so that one is also 27, and this one is 9, and that's 1. Okay, I think that's right. Might have made a mistake there, but again, that's not the key part. It's this, and hard to draw a straight line, and this here. Understanding how our nested functions work with function notation. All right, so a little bit of fun there. There are more. This is from our kind of Calculus Volume 1 textbook in here, Chapter 3. And there are more examples and practice questions and stuff if you want to do this. I guess I should quickly mention the honors math course, which is usually people would do in their second year. So you have a required statistics course to do in your second year. Honors math is optional, but if there are a lot of our the partnerships that SolBridge has with other universities, a lot of those require honors math. And that is that course is basically all calculus. So it's does these rules and then kind of goes from there. So if you want to do more calculus stuff, that's where more calculus is. You can do it anytime you want, but if you are going to do one of the partner study programs, like a 3+1 or a 2+2 or dual degree or something, then you should do it in your second year so you have done it early enough and you can do those other programs. Okay. All right, we'll leave it here. Glad we were able to get to at least some of this. And then we have a review class on Monday. Please remember to actually look at the final exam that I posted, the sample final exam. Try out some of the questions, and we'll talk about those questions on Monday. All right, we're done. Goodbye, everyone. I will see you on Monday.